So this set of problems deal with fracture mechanics and crack propagation. So the first question is: a steel plate has an elliptical crack of 10 millimeter length. You can see that here, a crack that is 10 millimeters long. External stress of 100 megapascal is applied, and the application of this 100 megapascal stress results in a stress at the crack tip here of 525 megapascal. Knowing that, what is the radius of curvature of tip of this crack? So we know from the equations that we've done in class that the maximum stress at the tip of the crack, the maximum stress that the material sees at the tip of the crack is a function of the applied stress. So maximum stress at the crack tip, which is given by sigma max, this value is a function of the applied stress, which is sigma naught, this is your applied stress, and then the crack length, which is your A, actually A is half the crack length. Remember, for an elliptical internal crack length is actually 2A. So 10 millimeters is in fact 2A. So A is half the crack length. And then finally, rho sub T is the radius of curvature of the crack. So rho sub T is the radius of curvature of the crack. Remember, if it's a straight, narrow crack, the radius of curvature of the tip is 0. For an elliptical crack or any other crack, there's a certain radius of curvature. You can see that the crack is curving at its tip. And if it's a circle, radius of curvature is equal to the radius of the circle. So given that, we need to find out the radius of curvature. So it's a simple, straightforward problem, just applying this equation straight away onto it. Sigma max is given as 525 megapascals, which is newtons per millimeter square. So make sure that you know that this is in newtons and millimeters. Sigma naught is 100 megapascal, 100 newtons per millimeter square, times 1 plus 2 times square root of A over root sub T. A is half the crack length. So that's 10 millimeters as 2A. So for A will be 5 millimeters divided by rho sub T. And you can do the calculations. You can simplify this and you will get a value of rho sub T, radius of curvature. Once you solve this, you will get this as 1.1 millimeters. So this will be the radius of curvature of this crack. Very simple, straightforward solution of this problem. .1 millimeters. Okay, so the next question is: a steel plate is used in a nuclear reactor that has a fracture toughness of 80,000 psi times square root of inch, and is exposed to a stress of 45,000 psi during its service. What is the critical length of an edge crack? So make a note of that. The question is asking for an edge crack here that will result in a failure of this plate. Now, the second part is crack is in the interior. What will be its critical length? So you know this equation K1C, which basically K1C is the fracture toughness. So this is K1C, fracture toughness is given as a function of a constant parameter y, right? Y is a constant, which is given as 1.12. It's a geometrical constant given as 1.12 for this problem. So that is your y. Sigma is the applied stress or the critical stress. That is sigma. And then A is the crack length. For the time being, I'll just say the crack length. You should know where the crack is to know what value you should take. So I'll just say the crack length. Remember, it's an edge crack. Therefore, A will be the length of the crack itself. Remember, edge crack versus internal crack. Edge crack, the crack length is A. If it's an internal crack, the crack length is 2A. So remember that. Knowing that, all you need to do is to do a simple replacement of numbers in this equation. K1C is given as 80,000 psi times square root of inch. Make sure that your units are consistent. Y is given as 1.12 times sigma is given as 45,000 psi. So sigma is given as 45,000 psi. Square root of pi times A. In this case, A is the, and that's what we have to find out. A is the edge crack length, which we have to find out. So if you do that, so this is the edge crack case. You can do that and you will find out that simply substituting this, you will get the length of the crack as 0.8 inches. Simply substituting it, you will get 0.8 inches. Now, the second part of this question asks you if the crack is the interior of the plate, what will happen? Remember, interior crack length is 2A. Once you found A, interior crack length is 2A, which is 1.6 inches. So that is, again, a simple direct application of this equation, the fracture toughness equation. The next question also deals with a very similar problem. Here, you're given a plate with a prismatic cross-section, prismatic meaning a rectangular cross-section, made using a material with a fracture toughness of 9,000 psi times square root of inches, exposed to an axial tensile load of 40,000 pounds. A load that is acting here is 40,000 pounds. Determine the minimum thickness of the specimen. So what you need is the thickness of the specimen that you need for what? To control the crack to a length of 0.5 inches. The crack cannot be more than 0.5 inches, internal crack. So something, if a crack like that forms here, that crack should not be more than 0.5 inches. What should be the thickness of the plate? So again, a direct application of this equation, K1C is y sigma times square root of pi A. And what you can do here is you have K1C given as 9,000 psi times square root of inches. Y, you can take it as 1. Now, sigma stress is not given, but what is given? Remember, this is exposed to an axial tensile load of 40,000 pounds. So this is an axial tensile load, that's 40,000 pounds, and it is subjected to that 40,000 pounds in this cross-sectional area that is 3 inches times the thickness. So instead of stress, I can write force over area times square root of pi A. I know the A that I need is limited to 0.5 inches. Remember, this is an internal crack of 0.5 inches. Therefore, my A will be half of that, which is 0.25 inches. Right? This is an internal crack that has to be limited to a length of 0.5 inches. So 2A is 0.5. If it were an external crack, you would put in 0.5 here. And F is known to you as 40,000 pounds. So everything is in consistent units, pounds and inches. So this is pounds per square inch times square root of inch. So that is good. This is in pounds. You will get the area in square inches. If you do this, you will get A as you will get the value of A as 3.93 square inches. So you get the cross-sectional area as 3.93 square inches. This cross-sectional area, the area of this cross-section is now 3.93 square inches. One side is 3 inches. Therefore, you can easily find the thickness of this plate. Thickness is equal to 3.93 divided by 3, 1.31 inches. 1.31 inches is the thickness of this plate. So again, 3 very simple problems for you to think over and do similar problems that are available in your homeworks as well as in the worked out problem examples.